Welcome back. In the last lecture, we pointed out particularly about the quality of service requirements for a given traffic, the voice, video, data. We pointed out only two, the loss and the delay. So loss is generally, what is loss? Some packet is not reaching the destination or it reaches erroneously. So it is generally what in the reliability. How reliable a communication is. Reliability means delivering the packets without any loss. Okay, so that is called a reliable link, reliable transmission. So you can bring it to the reliability. The reliability has to be 100% reliability for a source to be delivered there, and the 100% reliability is expected by the users. If any network is offered to them, they will ask reliability has to be 100%. Delay is the latency, so that is important in the latency, delay variation, everything is important in the latency, which is a round trip delay. Okay, it goes, and then if you use various mechanisms to to go to the destination and then returning back and so on. ARQ is one such thing. Similarly, many other round trip may be there. So delay, all this delay can be brought in here. Throughput is a data which has to be delivered in a given time. The rate at which a data amount of data that can be delivered, that has to be delivered in a given time. So that is throughput. People will expect, they may have a large amount of data to be delivered in a given small short time. So whether the network can provide this facility or not. So they expect the throughput should be this much. So for which the network should have wherewithals to deliver at that particular rate. There is going to be another thing is the data rate, maximum peak data rate and then average data rate. That means each service requires a minimum rate at which the bits have to be delivered at the destination without satisfying all the quality of service parameters. So this data rate, we will deal with it a little more detail when we talk about the wireless networks, because when many types of services are to be offered simultaneously, data rate requirement, peak data rate will be something, average data rate will be something for different services. I will come back to it a little more detail later. So generally, these are quality of service parameters. Now, data rate, let us try to understand. So, as we know, voice and video they originate as analog signals, so you need to convert to digital, for which digital source coding, I call it as a source coding. So this input can be a waveform, or it can be even discrete characters, discrete symbols, like digital, even digital. So it is a waveform, means it can be a voice or video. So you have to convert this into digital. This can be analog, digital. So here it has to be essentially digital. So digital means what? It can be binary, it can be any ternary, or it can be decimal also. So you can convert to anything. But we normally convert to binary and then deal with it. So how do we convert a source into a digital waveform, analog waveform into a digital waveform? For voice is analog, so it has to be discretized first of all. So you will sample at a twice the bandwidth of the voice. or if it is a video, that is also to be sample related. What is the bandwidth of the video signal? So you will have to discretize the samples in time domain, then quantize and encode. This will happen in both voice and video. A simple digitization process will involve sampling, quantization and encoding. Okay? Now for sampling, sampler requires one knowledge of the source. If it is a voice, it requires what is the bandwidth of the voice signal. 4 kHz. Now traditionally people consider it as 4 kHz. If it is audio, it is 15 kHz. They consider video 5 MHz. Okay? So you have to sample at a Nyquist rate. 8 kHz for voice, 30 kHz for say audio, and then 10 MHz for video. Simple, in a very simple manner, if you want to do encoding process, then each sample is to be quantized, because even after sampling, the signal is still continuous in nature. The amplitude can assume any value between a range. Still continuous. In the time domain it was continuous, so you sampled and made it discrete. So the time, this kind of waveform you sample at the periodic instances. So this is the value, this is the value, this is the value. Even after sampling, the sample signal is still continuous in voltage, but discrete in time. So you have to discretize in the voltage also. That is called a quantization process. So sampling, quantization. So you quantize using certain number of levels, and for each level you assign a code and then deliver it as a digital information. So what is the bit rate that ultimately will emerge? So for voice, this is not the one that is presently used. So why they are using different, you will understand. 4 kHz bandwidth, okay, 8 kHz sampling, and then 8-bit coding. Let us say 8-bit each sample, bits per sample. Therefore, 64 kilobits per second. Similarly for video, audio, let us assume 15 kHz, the 30 kHz sampling, and here again the same 30 to 80 before. I am only discussing about the concept. This is not the current standard. I am trying to impress upon what is the bit rate. So video 5 MHz, let us say, bandwidth, sample 10 MHz, and here again 8 bits per sample, and then 80 megabits per second. So this process is known as the pulse code modeling, PCM. You take a voice, sample at double the rate, encode using quantize and encode each sample by 8 bit, 64. So now you look at this. If you have to transmit voice across a network, the rate at which you have to transmit is 64 kilobits per second. For audio, 240 kilobits per second, video 80 megabits per second. If you use only PCM. But people have understood how to reduce this bit rate, compression. Okay, you can compress the voice, you can compress the audio, compress video, you can compress the data also. So you don't have to require 64 kilobits per second. You can compress it to a much lower bit rate. Now people are using 13.6 kilobits per second. So how do we compress? Do we remove certain samples from the signal and then represent? No. So what they do is they exploit certain properties of the signal. What is the redundancy that is present in the signal is exploited in the compression process. It means all the redundancy removal techniques are employed. In whatever way, if you are able to reduce the redundancy and encode only the intelligibility, then you will be able to reduce the bit rate. So a lot of compression algorithms are available in all these audio, video data. So there is a separate subject page. So multimedia compression, if you want to go through those techniques. I will come to the present day standard later, but what I am saying, digitized, you will get into this kind of bit rates. It has to be compressed using various technologies. So it has more or less matured. And in the whole process of compression, people exploit the signal property, redundancy that is present. That redundancy can vary also with respect to time. So all kinds of analysis people do. So they compress into very low value. So people are able to provide, if you look at MPEG video, the bit rate is very like 6 Mbps per second or even less. Depending upon the quality that you require, this can be reduced. Similarly, this can be brought to 13 kilobits per second or even less, 9.6 kilobits per second and so on. Now, there is an end to it. You cannot go on compressing. There is a minimum bit rate below which you cannot compress. That minimum bit rate is dictated by information theory, which is basically the entropy of this one, the entropy of noise, entropy of audio, video. Look at that will be the minimum number of bits required to be represented per sample, and the rate at which the symbols are coming, the bit rate will be also accordingly determined. So that is as far as the waveform encoding is concerned. This is called source coding. In digital communication, you have this source coding. Waveform is converted to digital. Similarly, text also will be encoded digital to digital. That is also called source coding. In the text, again there are a lot of redundancies. Like in English text, if you see, a lot of redundancy present, which can be using Hoffman coding, arithmetic coding, and there are many impulsive coding. There are many other coding schemes available, using which you can compress the digital text into another digital text, but the number of bits required to represent the text will be less, and therefore number of bits required to be transmitted per second will also be less accordingly, and therefore bit rate will be less. Okay. Now bit rate, this is the requirement of the source. The source expects latency has to be within a limit. It expects bits are to be delivered within certain time frame successfully and reliability, and then each service requires specific data rate to be delivered. Now, how this is met by the network? This can be met only by providing a sufficient bandwidth. Okay. Now, let us say bits are coming like this. So, say 1 1 0 0 1 0 some. This may represent data, voice, video, whatever it is. So, if you represent this electrical waveform like this, okay, like this, 1 1 1 0 0 1 0, something like this. What is the bandwidth required for transmitting this type of waveform? We already in the last lecture we discussed about the bandwidth required. If the baseband, I am going to talk about the baseband waveform. This is a baseband waveform. Bandwidth required depends upon the data rate. Now it is 64 kilobits per second. Suppose voice is 64 kilobits per second. Okay. So corresponding bandwidth required is approximately 64 kilohertz. If you look at the power spectrum like this, okay, 0, and as I told you the other day, this is the bandwidth, so 64 kilohertz. minus 64 kilohertz. Okay, roughly. This is roughly if it is the baseband transmission like this. If you choose to represent digital data using this type of a waveform, for a 1 there is a 1 pulse, for a 0 a negative pulse and so on, then the bandwidth required will be something like this. But this is not the best way of representing digital data in electrical form. There are many other ways called line coding, you must have heard about. So instead of representing like this, you can, the best way of representing is even if you provide this bandwidth, there is going to be indivisible interference which has to be corrected later on. The best way is a sin x by x function, sinc function for each of positive sinc function for the 1, negative sinc function for the 0. Bandwidth will require is half of this. So if you represent each of these bits using sinc function, okay, sinc function, which is something like this. Okay, 0, and exactly at this point another function, this point another function. You opened it. Of course, I am not going to the details in the subject itself. Then it can be shown that the bandwidth required is 32 kilohertz. If it is 64, if you use this waveform, it requires 64 kilohertz. If it is appropriately in an optimum manner, if you select a waveform for representing this, it requires different lesser and lesser and lesser bandwidth. So, bandwidth is a resource, as you must have heard about how the bandwidth is auctioned and how much cost it experiences in every 4G, 2G, 3G, 4G and 5G. Bandwidth is auctioned. I will come to this later on. So, bandwidth is a cost. So, just because we have very casually selected a waveform, we require a bandwidth like this. But if you intelligently select the waveform for representing this, then the bandwidth required can be reduced. Now, when you talk of wireless communication, you need to go for modulation, and this bandwidth will be around the carrier. Same if you represent like this and then modulate on the carrier, then this will become FC. So around the FC plus 64, FC minus 64. Bandwidth required is double. In that case, this is FC minus 64 and that is FC plus 64. So in a one particular modulation, okay, this bandwidth required will be for 64 kilohertz, you require 128 kilohertz and BTSK modulation, for example. There also, if you can select the waveforms appropriately, bandwidth required can be reduced. Okay, using the QPSK and then Emery BSK and other modulation schemes, people have shown bandwidth required can be even reduced further. So, why I am saying bringing this point here is, for representing any traffic in the digital form, you resort to sampling and other compression, etc. It ultimately results in a bit rate. Now, those bits are to be transmitted across the channel, and for which electrical waveforms are required, and people have spent their lifetime in selecting optimum waveforms which requires less bandwidth, and they have shown, they have proved that certain schemes require less bandwidth, but it requires to be transmitting more power in order to achieve the required quality at the destination, and a trade-off between that. If suppose a waveform is selected, it requires certain bandwidth for transmission and to deliver at the destination with required quality, certain amount of power. There is another technique which requires more bandwidth, but the power required will be less, but delivering the same quality. So there is always an exchange between the power and the bandwidth. which if occasion permits we will go later. So while selecting modulation schemes, in other words, while selecting the waveforms for transmission, people have kept in mind the amount of bandwidth that it occupies in the channel and amount of power it requires to be transmitted to deliver at the destination with the required quality. So that is, what is the relationship between bandwidth and the bit rate? So the bit rate is say RB bits per second. No one can tell what is the bandwidth required. It all depends upon what type of electrical waveform you selected to represent those bits. So sometimes people get confused regarding bit rate and bandwidth. Okay, bit rate, bandwidth. They are related. Definitely, they are related. So if the bit rate is known to you, if someone asks you what is the bandwidth required for transmitting these bits through a particular channel, then next question is what type of modulation will you use, what type of particularly modulation you select, then only they can tell you what is the bandwidth required for transmission, what type of baseband waveform you select. Okay? So depending upon type of electrical waveform that is selected, bandwidth required along the channel will vary. So bandwidth and bit rate are not the same. Suppose bit rate, bandwidth, okay? This is modulation. Small one example. Now, if you select what is known as a BPSK modulation, suppose our bit rate is 64 kilohertz, in this case, bandwidth